Satellites provide important networking in today's internet for always-on connectivity in remote locations. And in addition, during disasters where wired infrastructure might go down, satellites provide connectivity. And their bit rates have been increasing about 20-fold recently. However, latency is still a challenge. Basically, it takes about 300 milliseconds to bounce a signal up and down for a geosynchronous satellite. So about a 600 millisecond round trip time for a network connection. And that latency is a challenge for TCP bit rates. So from your networking class, remember TCP sends 1 window's worth of packets every round trip time. And so that round trip time is high for a geosynchronous satellite network. And the window size itself, though, depends upon the congestion control algorithm. So we compare 4 congestion control algorithms in this paper, in this work. TCP cubic, sort of the traditional loss-based approach. BBR, a newcomer developed by Google that computes the bandwidth delay product and uses that to determine the window size. PCC uses a utility function to determine the window size. Then Hybla is satellite optimized for high round trip time algorithm. And so there's been few published studies of TCP over satellite networks. The ones that do exist are mostly simulation or emulation. So here we have a commercial satellite network, and we're going to use that to measure the effect of the congestion control algorithm over satellite networks. So this is a brief outline for this short talk. As my introduction, I'm going to talk about the methodology in brief, then results and conclusions. So this depicts our test bed. We take a satellite network. We have it connected on the roof of our research lab, so we can bounce it off Viasat's geosynchronous satellite. And then we send data from our servers, which are actually also WPI, but they cross the internet, and we have then a last mile connection to our isolated. So we have about 24 hours of traces using each of the 4 protocols that we discussed. So I'm going to talk about those results just in brief. Again, refer to the paper for more details. We have some baseline results, and I'll talk about steady state and then startup. So for baseline results, this depicts about 2.5 days of time for the satellite network, where we have none of our bulk download traffic. We're just doing a UDP ping to see what the network's like. And this y-axis now is delay, so in milliseconds. And so you can see that, again, the floor, the minimum is about 600 milliseconds or so. And it looks like there's a fair amount of variation, but if you look at the summary, the stats in the top, the summary, the mean and the median are both really close to that 600 mark. And so there's actually not much statistically, and it just exaggerated in the graph, but there are these really large spikes you can see. We do have some spikes that are well over a second, even over 2 seconds. Loss rates are really low. There's very low loss, 0.05% loss, and most are just single packet. Largest there is about 11 packets, about 2.5 seconds of outage, if you will. Okay, so a quiet network, low loss. So to that, we then do our bulk downloads throughput. So this is steady state once the protocol is warmed up. This is the throughput achieved. And so I have just 2 depictions here. These are shown with box and whiskers plots. So I have the mean on the top, the median on the top, the mean on the bottom. So on this axis, I have each protocol. So the BBR, Cubic, Hybla, and PCC. And so again, run serially, so not simultaneously serially. And this is the result of 24-hour traces for each protocol. And so these are shown with a box and whiskers plot. So box and whiskers shows you the distribution. The interquartile distribution is that box. And so we can compare across protocols. So starting with the median, you can see that the medians are all pretty similar, maybe with the notable exception of PCC here, that has sort of a lower median and a slightly larger distribution of median throughputs. The means vary a little bit more with BBR and PCC, again, having the lower mean throughput, and Hybla being the highest, and Cubic being slightly under that. So this is a table that sort of depicts those results. We also showed on the table is the round trip times, because you care often about both. So how much round trip time do you have, which is, again, that baseline round trip time plus queuing. And so we can go ahead and compute the effect size. So if you took Cubic as your default and you changed it out to one of these other protocols here, what would be the effect on performance? So this is the throughput effect size from changing the protocol. And so again, a large effect is something about these values of 0.4 to 0.7. These are large effects. And in fact, changing to BBR has a large effect in the downward direction. The throughput is noticeably lower, so a large effect in changing that. Hybla would be higher, and then PCC lower. And so all these results are significant at the 0.05 level. So we then can also look at startup. So startup, again, is how long it takes to ramp up to throughput speeds, where here you're often concerned with downloading, say, a small object, like you're doing a web transfer, really small objects on this side, some small object, and you want to know how long that's going to take. And so that's what this graph depicts, where this is the download size, and then this is how long it takes to download an object of that size, where again, higher is worse. And on this graph, each point is the mean value shown with a 95% confidence interval. And the top trend line here then is cubic. So cubic has the sort of the worst performance. It takes the longest to download, the slowest to start up. And this bottom trend line is Hybla. So Hybla is sort of the best. And then PCC and BBR crossover. So there's a sort of a trade over where PCC is doing a little better initially, and then BBR is doing a little better for sort of slightly larger object sizes. And so again, this is a table. You can summarize the startup and the RTT values. And again, significant at all levels to take an effect size versus the traditional cubic as a default. And here the effect sizes are actually very large. Those are very large effect sizes. There's a big difference in swapping protocols, if you will. And they're all in upward direction from BBR to Hybla to PCC. So we can actually take those two values I hinted at, so the throughput and RTT, and you often think about combining them, meaning higher throughput's good, but if that's at the expense of higher round trip time, maybe not as good. And so the power metric takes the throughput and divides it by the round trip time. So we can compute the power metric for all four protocols, and we can now do it for each state. So we can do the steady state, we can do the startup state, and so here's each protocol, and those are the actual computed power using that metric. And here I've highlighted the two that are the most powerful for each state. So during that startup state, Hybla is the most powerful, had the highest throughput, had slightly higher RTT, but the throughput significantly higher for that startup state. PCC had the highest power for the steady state. It actually had the lowest throughput. You remember that mean lowest throughput, but it also had a very low RTT. So it ends up being sort of a high power by this metric. So that's a quick summary. So again, satellite connection, a very consistent 600 millisecond RTT as a baseline with low loss. At steady state, of the four protocols we compared, they all have a fairly similar median throughput. PCC maybe a little bit lower. The mean throughput, BBR and PCC are the lowest two, with cubic and then Hybla being a bit better. At startup, Hybla was the fastest, BBR and PCC sort of the next, and cubic the lowest. For power, PCC has the most power during steady state, and Hybla has the most power during startup. Again, take a look at the paper for details. Future work areas, a bunch of things we're currently working on. Multiple flows, so how do flows compete over this last mile link, say BBR and a cubic together? We're also looking at different settings. You can tweak TCP in lots of ways. Hybla has this RTT 0 setting, that's what lets it scale. And then the other protocols such as Quick, how do they perform? And performance enhancing proxies are often used to split that link in the middle to try and help out with the satellite link. So investigating performance enhancing proxies for the satellite. And then other applications, I sort of hinted small download. So how do things like web browsing perform, and things like streaming video and maybe games.